Hello everyone. Today we are going to discuss about frequency response analysis in control system. This is our fourth chapter. So at the end of this video, students will be able to find the frequency response and also analyze the frequency response and time frequency domain specification with the derivations. What do you mean by frequency response? The response, it is nothing but output it is in terms of frequency. The steady state response of a system for input sinusoidal signal is known as frequency response. This is the general meaning of the frequency response. If the input of sinusoidal signal is applied to the system, then the output is also a sinusoidal signal. Input and output of a sinusoidal signals have the same frequency but different magnitude and different phase possible. If you are taking open loop transfer function g of s, while substituting s equal to j omega in this transfer function, we will get g of j omega. It has a magnitude and phase. Similarly, for the loop transfer function and also closed loop transfer function, it is denoted by ms, m of s. After substituting s equal to j omega in the closed loop transfer function, we will get m of j omega. It is also having magnitude and phase. That is a mod m of j omega and angle of m of j omega. Frequency response analysis has having advantage and also disadvantage. The frequency response of a linear time invariant system is independent of the amplitude and phase of the input test signals. The design and parameter adjustment of the closed loop system for a specified closed loop performance can be carried out easily in frequency domain compared to the time domain. The effect of noise disturbance and parameter variations in the frequency domain can be easily visualized. There is a correlation between time domain and frequency domain specifications, so that the time domain specifications of a linear system can be easily predicted from the frequency domain specifications. The transfer function of a system can also be obtained from the frequency response methods. It has a drawback, that is mainly the methods which are considering for obtaining frequency response are outdated, you can say old one, as compared to the newly developed methods for modeling and simulations. These are the advantages and disadvantages of frequency response analysis. In the frequency domain, we have some specifications to describe the frequency domain, frequency of the particular system, similar to the time domain specifications like rise time, delay time, peak overshoot. In this frequency domain specifications, these are the main specifications. Resonant peak is denoted by m suffix r. The maximum value of magnitude of the closed loop transfer function in frequency is known as the resonant peak. When we are comparing, because it is having relation between time and frequency domain, we compare these two. A system with a large resonant peak will exhibit a large overshoot. Here, overshoot is the time domain specifications. In general, the magnitude of resonant peak gives indication on the relative stability of a stable closed loop system. The resonant frequency, it is denoted by omega r. It is the frequency at which the output of the system has maximum magnitude is called resonant frequency. At this frequency only, we can get a resonant peak. And next one, it is a bandwidth. denoted by omega b. It is the range of frequencies at which the magnitude drops to 70.7%, or we can say minus 3 dB from zero frequency value. So next, we'll go for the derivations. Derivation of frequency domain specifications. We'll start with the resonant peak and resonant frequency. Let us consider a standard second order system with closed loop transfer function is, that is m of s, is equal to c of s by r of s, that is equal to omega n square by s square plus 2 zeta omega n into s plus omega n square. First thing is, because it is a frequency response, we need to convert into frequency by substituting s equal to j omega. After substitution, we'll get m of j omega, that is equal to, so omega n square by, just substituting s equal to j omega, wherever s is there, just substitute that value. We'll get this. Then, just separate omega n square in the denominator term and cancel these two. We'll get here 1 over 1 minus omega by omega n square plus j into zeta omega by omega n. Let us take a normalized frequency u equal to omega by omega n and substitute this value in the above expression. We'll get m of j omega is equal to 1 over 1 minus u square plus 2 zeta j into u. This term, it is having real and imaginary part. Basically, it is a complex term. So, it has a magnitude and phase. Now, in this case, we need magnitude. So, let us take magnitude here. Magnitude mod m of j omega. So, that is 1 over square root of real square plus imaginary square. Just to substitute, that is the real value here, 1 minus u square, and imaginary value 2 zeta u. So, that is equal to square root of 1 minus u square whole square plus, so 4 zeta square u square. So, we know that how to find the maximum value. So, by using maximum conditions. So, by using that, is the dm by du is equal to 0. So, we will get only maximum value at resonant frequency omega equal to omega. That is nothing but u equal to u. Now, first to differentiate with respect to m with respect to u and equate to 0. After that, substitute u is equal to ur, in that you will get the ur the value from this. Just simplify here. First, differentiate m with respect to u and you will get this value, and substitute ur, that is a value, you will get. Simplify those expressions. You will get here ur square is equal to 1 minus 2 zeta square. So, therefore, ur is equal to square root of 1 minus 2 zeta square. Resonant peak occurs when ur is equal to square root of 1 minus 2 zeta square. Put this condition in magnitude value and solve resonant peak value. So, when you are substituting u is equal to ur, automatically that m is equal to mr. Let's substitute that value in the magnitude, you will get a resonant peak. Mr is equal to 1 over, just substitute u equal to ur in that condition and simplify that, you will get the expression, that is 1 over 2 zeta into square root of 1 minus zeta square. So, therefore, resonant peak, it is denoted by mr is equal to 1 over 2 zeta into 1 minus zeta square. This is the final expression for the resonant peak. Similarly, we can find the resonant frequency, because at this frequency only we can get the resonant peak value. So normalized resonant frequency UR is nothing but omega R by omega N. Already we know from this, that is already we find the value, we found already UR is equal to square root of 1 minus 2 zeta square. So that is equal to omega R by omega N. So from this, simply just cross multiply, you will get the value of omega R. So omega R is equal to omega N into square root of 1 minus 2 zeta square. So that is nothing but resonant frequency. This is the another simple derivation for the resonant frequency. Next one, so from the equations of both, you can say here resonant frequency and resonant peak, you can conclude that as this value, that is the zeta value, I can say here zeta as zeta is okay approaching to 0, MR is greater than, that is the resonant peak is greater than the 1, and omega R is less than the natural frequency. Natural frequency. When zeta is greater than 0.0707, there is no resonant peak. We won't get any resonant peak if zeta is greater than 1 over square root. Okay, if zeta is approaching to 0, MR resonant peak approaches to infinity because both are, so that is MR is directly proportional to 1 over zeta. That's why MR approaches to infinity and omega R, that is the resonant frequency, approaches to omega N. Now, and third one, it is a bandwidth. Okay, bandwidth, it is the range of frequencies up to the cutoff frequency, beyond which the magnitude drops down by 3 dB below zero frequency level. So again, let us take normalized bandwidth. UB is equal to omega B by omega N. Already we know magnitude. So that magnitude is equal to minus 3 dB. That is nothing but 1 over square root 2. So in this magnitude expression, substitute UB value in place of U and equate to 1 over square root 2. So that is the expression here, M equal to this. Square both sides and cross multiply it. You will get the expression UB for 4 minus 2UB square into 1 minus zeta square minus 1 equal to 0. So because it is a fourth order system, let's take x equal to UB square and you will get quadratic expression. So solve this quadratic expression, you will get x value. Let us take positive value. From that, UB equal to square root of x, and then UB is equal to square root of x, substitute that value here, and that UB is nothing but omega B by omega N. So omega B is nothing but bandwidth here. From this we can find the bandwidth. Okay, so now we have discussed about what do you mean by frequency response, what are the advantages, disadvantages, and also the frequency domain specifications. Okay, thank you.